1, 2. 1, 2, 3. Sound check. 1, 2. Hopefully sound is better than before. I have only one microphone is on. Video is rolling. And we should be live. Okay. Is the sound quality good? And hello everyone. Today we will take a look on this 3458A, which is HFL edition. It's quite a rare beast, but as usual it has a bunch of problems, so we will take a look at internal boards and do some circuit level repairs, hopefully. Okay. So let me do a quick check that I have everything ready, and then we can go ahead and try to fix this one. All right. Yeah, it's pretty good to have some room, but it's getting filled up with more stuff as we speak. So I think this will be the most space where we'll be testing the meter, and that bench is mostly for checks and calibrations, and there is my large temperature chamber back on the further bench. So we'll talk about what's wrong with this unit. So this instrument have DC voltage issues. Well, it had it originally, and now they are fixed a couple days ago. And it also have AC problems, so we will have to take a look on those and see if we can fix AC issue and do the full self-test, get it to pass, do the artifact calibration, and do some comparisons against my other standards and 3458As. So it's actually the problem with the DC voltage was it was given as soon as you start the self-test or run the artifact calibration. It was given reference loop error and would not do anything else. So that was caused by a bad multiplexer. I can show you on the another A1 board what multiplexer was the culprit. Let's see it. So the multiplexer was on the A1 board. This chip right here, it's used for resistance current source, which is all this section, but also it was routing the heater output from A9 board, reference board, through this multiplexer. Was used for self-diagnostics and tests. So this is usually DG211. I didn't have DG211 on hand, so I installed a better replacement, analog device ADG441. And after that, all the DC voltage issues and self-test issues with voltage ranges were resolved. And as you can see now, the meter is actually logging 10 volts. So I can zoom in a little bit more. So the display on this instrument is fairly dim, and I have a lot of studio lights, so it's a little bit hard to see. Perhaps I can reduce, there we go, a little bit overexposed, but you can see it's reading 10 volt from my reference, and it's pretty close to actual value. The actual value is 999999698. But that was the value calibrated a while ago, because if we can see on the other meters, the ones in my stack over there, you can see they all kind of give a little bit different values. It's also a little bit warm today. It's around 25 degrees centigrade in the lab. So those three 3458As are connected to the same reference. It's the cable that's sneaking into the thermal chamber that sits at 23 degrees constant, and then this gray cable connected to the front input of the instrument that we will be talking about and fixing today. So that's the thing, and I would like to say hello to everyone who is joining our little chat here. Hi Ian. I might actually show you that PDVS Mini is still here in the lab, and it's quite handy too. Very small form factor, battery powered, and can supply up to 10 volts with a very nice resolution and precision, thanks to integrated LM399 reference. So I use this source for various projects in past year, and it's pretty handy. It's not super metrology grade like would be the 5720 calibrator or anything like that, but it doesn't also cost $30,000. So if somebody is looking for a little metrology source, these are very nice units to have in the lab. So you can get them, just Google for PDVS2 Mini voltage source, and you will easily find posts and a web page where you can get them. So, yep. All right, so let's see what's the issue with the meter is. I can show briefly that it's indeed logging just fine. So there is the data log. You can see the D purple in actually magenta. It's reading from this meter, and the standard deviation for the last 60 samples is 414 nanovolts, which is pretty decent. So the A, B, and C are my other 3 meters. So we can stop this, go back to the meter and see what it does if we try to do a self-test. So it's running. Actually, before we do that, we can check the revision. So it's running revision 9.2. That is the latest firmware for the instrument. And 2 is also shows that the A3 ADC board have the updated firmware. So for the very old board, it's 1 in there. So let's try and run a self-test. So DC voltage is tested first, and originally that was the first second after you initiate self-test. It failed. Now it's obviously passing. I didn't test the ranges like 1 volt, 0.1 volt, 100 volts, and others. But I think we should fix the AC voltage problems first, and then we can do the full test on all the ranges, all the functions. So there we are. Self-test failed. So we can check what actually failed by pressing Shift error. And then there we have generic code number 204 and more details. If we scroll to the right, hardware failure, flatness duck, convergence, and here is the number 198. That is the constant from calibration HP calibration manual that outlines what range and what point actually failed. So we can run the self-test again just to confirm that it's consistent. There we go, failed again. So I can also probably show, okay. So the error that it gives, 198 is flatness DAC, 10 volt. So this is base range during the ACAL AC. It also executes this calibration step. We can try the artifact calibration, but I'm confident that it will fail as well. So error is the same. And we can do the ACAL DCV, just self-adjusts and calibrates DC voltage ranges. This passes fine on this meter. ACAL ohms also passes just fine, but ACAL AC fails, and we can run all just to show, but it will actually fail during the ACAL AC step. Usually artifact calibration autocal takes about 860 seconds on these meters, so it takes a couple minutes to run. And meanwhile I can open up schematics so we can have it handy. Alright. Unfortunately, I don't have a spare A2 AC board, so we can't easily swap it with the donor part. But actually, we might take apart one of the other meters, that top one over there, if we're really desperate. But we'll see if we actually need to go that route just yet. And there are some savvy people already suggesting that it's either main Elantec EL2039 or dual JFET on the input. Well, there is a twist, because I actually took this meter apart before, and I know that it might not be as simple. So you'll have to hang for a couple more minutes to find out why. ACAL resistance, ACAL DCI. It will fail soon enough. So the another point is why I wanted to make a video about this meter is it have option HFL, and what it means is sometime around year 2000, probably a little bit earlier than that, Fluke partnered with HP to have a special version of 3458A, which would Fluke sell under their brand. So it was like you go to Fluke and you order this meter, and you essentially get HP3458A meter, but with more selected A9 LTZ 1000A reference, and also it had updated 40 kilo ohm Vishay resistor for its main resistance reference. So there are no other changes other than like a sticker label with HFL and the box marked on the back that shows its HFL option, not the standard unit. A9 reference was actually sold by Keysight some time ago, not so long time ago. I think they still had it available in 2018, but recently, since they started working on Roche's Black Edition 3458A, they obsoleted HFL reference, and even though it was selling for around $2,000 and just meant better selection, otherwise it was still exactly the same components, exactly the same resistors, exactly the same super hot oven temperature setting point. So there was no hardware changes, only the selection for a better part. So ACAL DCI, 1 amp range. I think after that it will still have a couple steps, and then it will start doing ACAL AC, and it will fail. Also, Fluke actually, that modification for 40 kilo ohm resistor was made standard in all later units by HP, later Agilent, and later Keysight. So other than reference, there is no, like, if somebody is looking for the 3458A to use for the resistance measurements, you can get any later version of 3458A, like Agilent branded or Keysight branded, and they all have updated, improved resistance standard in them. So there is only essentially the difference is better selected LTZ1000. And most of the 3458As, like if you have them running 24/7 and in nicely controlled conditions, not abusing them very much by putting in the racks with a bunch of other hot equipment, then their reference most likely, not all of them, but most of them, would have annual drift less than 4 ppms, and often even less than 2 ppms. Especially if the modification to reduce the oven temperature is lower than standard, by installing 400 kilo ohm resistor in series with 15 kilo ohm original resistor on the A9 board. So what I expect to find broken in this unit? Well, I expect something on the A2 board. So we will take a look on some input signals and output signals and figure out what's going on. Zero DCI. I believe the next one will be AC. So let's give it a couple more minutes, and then we put it in the surgeon table and take it apart. There are a couple more projects and new things in the lab. So the Lakeshore that we looked at some secret live streams before, right over there. I'll be coming back to that project with some new cool things in hopefully nearest future. So we'll have also some DC resistance metrology stuff, because I just had my 10 kilo ohm ESI SR104 calibrated at very low uncertainty by a very nice lab. So that will be coming next. And yeah, we still have some poor Keithley 2002 waiting for the love right over there. As some might actually notice, it have a little bit unusual range. Sorry with the focus, I'm still doing this by hand with my manual focus lens. Maybe at someday I'll be getting the proper video setup for YouTube stuff, but I'm still not sure which camera would work the best for my needs, so I'm still using my 7-year-old DSLR for this stuff. So for those who don't know, what is going on right now here is meter is actually trying to adjust all its internal ranges and functions to the, here we go, and there we have our error. So the meter was adjusting all the internal functions and ranges to reference sources that are ultra stable DC source and ultra stable resistance. So let's see what the error is. Local error, shift error, my bad. Hard valve failure, flatness, dark convergence. 198, exactly the same as we had during the self-test. So let's take it apart. Turn it off. Now we need to disconnect our DC source. There is also a couple of mechanical issues with this unit. As you can see, the edge binding posts are really flapping around because the screw point is broken on them. So somebody probably hit the meter in the front, and that caused the damage for the plastic housing of this whole binding post stuff. I actually have one on the test cable that I use, so I can show that. So you can see it's like one overmolded piece with the nuts on it, and all the copper posts actually hard pressed into the plastic. So like if you have this or this mount hole broken, then there will be no way to mount this onto the plate, and there was another piece, plastic piece on top of this that covers this. This is just adapter I have used for some experiments, just HP posts and horrible banana dual plugs on the other end, and all with the Teflon cable. So all right, let's move it on the other bench and see what's inside. There we go, should be all right. So we can see I already removed some screws and some stuff. Let's have a closer look. There we are. So first off, we can notice that this meter have older version of CPU board. This is the CPU board that handles all the processing. Here's the main processor right behind this label. It's a good old Motorola 68000. So we have a single firmware chip right over there, this chip with the label, and have two non-volatile RAMs. These are Dallas DS1230Y 150, manufactured from 2011, week 23, and also the calibration ROM far on the back, this chip right here. It's Dallas DS1220Y 150, manufactured 41st week of 2010. So then we can take a look on A1 board. There we are. So the board doesn't have any special stickers or anything. It still have the standard part number of usual 3458A A1, which is 03458 66501. So we can see the resistance shunt that I was talking about. It's also resistance shunt and also resistance standard for all the resistance ranges. It's located right over here. It looks like a crystal oscillator, but it's not. It's hermetic V-shape VHP 101 40 kilo ohm resistor. Perhaps I should change to macro lens, maybe. Or maybe just easier to move a meter a little so we can see it from the label. There we are. So I can zoom in real hard, and there we have it. And if we can shine some light onto it, so this resistor is manufactured in 22nd week of 2006, standing on its legs. And we can also find all the other current shunts for like 1 amp range. This black ceramic body 4Y resistor. Then we have this black one is for 100 milliohms. This red one is for 10 milliamp, and then a couple of others, 1 milliamp, 100 microamp, the blue one, and then the 100 microamp is 40K, and then the high value low current shunt right there. So there is no other changes on this board. It looks pretty much like a standard A1 because it is. So actually I forgot to mention one more thing. Meter also had another issue originally, which was not working resistance measurement. So that was fixed before. Let me change so it doesn't, it's actually worse. Have this glare. Okay, that's better. Now we get the focus back. There we are. So the issue was with the Y resistance was not working. This op-amp, it's OP07, was getting real hot. Probably was dead from some overload event, and none of the resistance was working. So it was replaced with a different new 07 OP07, and then the resistor was fixed, but the reference loop issues still were popping up. So after replacing this switch analog multiplexer, the issue with the DC voltage was resolved, and we can take a look on the DC reference. So we can indeed see that this is actually have a little bit interesting tidbit. One can see a part number. It's actually a sticker. Says 034591006, but actually if we peel it off carefully, ta-da! Well, this is a sticker under it, 3458A 66529, which is HFL reference part number. Standard reference have 3458 66509, and better stability 002 option have 66519. So it's kind of interesting why it have the custom part number. And I know that high voltage option H01 also have part numbers with the 9100 numbers in them, but this unit does not have the H01, which involves more tested and probably treated especially A1 board, A10 board, which is the front and rear switchboard, this one, and I believe A2 board is also different. And just to show you the sticker option, there is our option labels. So it says empty options 001, 002, 700 and special, but it have marked HFL, and the part number, serial number is 27039. You can see it's indeed Agilent unit, have new style filter, and everything else is pretty much usual. Nice looking posts on the back, like nobody used them, which is probably true. I also can see, it's hard to see on camera, but I do notice that actually this chip and this chip, they were replaced before, either serviced by previous owners or serviced at Agilent, because when I removed the A1 board before to replace the multiplexer, I've seen some flux and residues from soldering that were not cleaned up around those chip pins. So that's what we have on the A1 side. Let's flip it over and see on the A2 board and ADC board. If somebody have any questions, then we can talk about it. And LM339 is not the power regulators, it is the should be the comparator. The power regulators are usually like 307, LM317 and 337. So close, but not quite. Okay. Some chips are falling out. There we are. So here we see our section of the outguard power supply, which is all of this stuff around here. We have the Schaffner. It's manufactured in 2000, year 2000, week 27. We have input diode bridge, some power regulators. This is a DC-DC supply for the vacuum fluorescent display. We have the in-guard crossing controller, some opto receiver and transmitter, power switch right here, and beeper over there. So here we have A4 board. I actually already tested this board before. It's working fine. No issue with the power on this meter. And then we have A3 ADC board. It's rather updated revision. Already with new style, you can see I was already here. I didn't bother to connect these external trigger fibers, well, because they are not related to the functions we care about right now. And also our suspect is right over there, A2 board. So let me get the camera straightened up. There we are. So I put already a label, flatness DAC 198 is the issue we have, and we can remove the protection cover from all the sensitive nodes. Ta-da! We are in like Flynn. And surprise, surprise, there is no EL 2039. Why? Well, because this is a newer board. It's date code year 2000, based on the chip markings. We can take a closer look. If I change to the macro lens, let's do that. There we go. Do we have the video? Yep, we're back in business. So we can see on this PCB the good old EL2039 was replaced with this tiny TSSOP chip. So it would be a little bit more interesting to test and check if actually that comparator works or something else is bad. We can take still a closer look. Whoop. There we are. We can probably even see the marking of the chip, which I bet is a Texas Instruments part. So let's see who is the fastest one to Google up what chip is that. Whoop. Well. It's the marking, I believe, is TI61ADK. Let's see, Texas Instruments part number decoder. Let's start with ADK first, look up. And I believe we found it. It's package DGN, 8 pins. Sounds about right. Let's see. Package pin size. DGN, HVSSOP, yes. Not sure if I can resize this. Sorry about this doing live. But there we go. It's the There we go. THS4631 high-speed FET input operational amplifier. It's high voltage, high slew rate, wideband FET. What's 210 megahertz gain bandwidth product. Slew rate 1000 volts per microsecond, 7 nanovolts per root hertz. Rail to rail, no. So it's rather fast FET amplifier, one channel. We can see the typical circuitry used for as a amplifier for low current fast photodiode. So yeah, that's the part that was replaced. The good old EL2039. All right, so what we can do is we can take a look what else on this board and start some probing. So what else we have in here? We have all these floating resistors and SMD capacitors with legs for the high frequency stuff. And we have some AD3528, which is also a deck, I believe. And there should be another somewhere. Yep, right there is another one. And we have also another Elantec chip on this board, but it was replaced with SMD version of Elantec on this Piggy board. So that is also newer patch. And I also love how the HP engineers thought about putting some spare fuses. So there are actual working fuses in here, these two, and spare fuses right there, in case you blow up a fuse. So you can just take one from the board. Very cool. What else? We have some lonely ceramic chip, which is AD6. I don't remember what that one. 637KO, I believe. Some DG211 switches, and also this hermetic stuff is Motorola SD4753, and the guy on the top is, let me check the label real close, it's LS591. I believe it's linear systems part, which is not easy to get or to buy. All right. So what we can do, we can power on the meter and see what signals are coming to the amplifier and out of it, and try to find where the problem is. So I believe I'll need to change the It should be all right. Okay. Do you have thermal camera? No, actually I do not have the thermal camera in this lab. But I don't think we will see much by thermal camera, because high-speed stuff tends to run hot even in normal operation. So without having the reference, like how hot the stuff should be, it wouldn't be as helpful. What we can do is print the actual page of the schematics with A2 board, so we can write down voltage and measurements results on that page, and it will help us to troubleshoot and visualize what's going on a little bit easier. So let's see if we can do that. And I'm very happy to have A3 size laser printer, so we can actually print decently sized schematics, and without requirements to have a microscope to use them. All right. Oh boy. Of course, it would help if I select the right feeder to print stuff. There we are. It should be good now. The page is just one page. All the A2 AC schematics is in there. It's rather dense. There we are. And again, this is schematics for the very first original 3458A. And it doesn't actually quite have all the changes and modifications made for the newer versions, but it's essentially the same functionality, and most of this stuff is exactly the same, so good enough for our purposes. So let's power it on and do some measurements. And of course you will not see anything because of the camera lights and all that, but actually it does indeed work. And to do the measurements we will use my good old Tektronix right over there. So I'll probably leave the camera running like that for now, and we'll comment on what I'm doing and what's going on. So let's change some configuration first. What we can do is set the channels. So I'll use channel 3, which have connected 10 this is just standard passive probe. What else? I don't think we need other channels for now. Channel 3, 1. So what we'll get here, that's a lot of noise. Yeah, there's the high voltage probe, and our, let's do 3 volts per division, center. There we go. And since all the front end of 3458A is isolated and floating, then we can actually use our ground, main ground, signal ground, as a reference from oscilloscope, and then do all the probing around, and it's safe. but if you fixing some power supply, especially like high voltage ones, then that could be dangerous, and you could danger blowing up your scope or getting electroshocked. So always pay attention what you're doing and understand how the grounding works and how everything should be connected. Okay. So let's see if I can get some of the glare from the light. That would be much nicer. It's better, it's worse. Yeah, I guess that is better. I'm trying to get, there is a test point for a low right in there, and trying to get the camera to see it. There we are. Okay. I need one of those Louis Rossmann repair multimeters to show the readings on the live stream. Okay. Actually, also one more thing I wanted to show is it's possible to see the error even without running the self-test or any other stuff, just by switching to AC voltage measurement, and then you're going to the 1 kilovolt range, and you can see some like 23 volts AC. That is definitely BS and not true, because nothing is connected at the inputs, so there could not be 23 volts AC in there. And then the same you can see on the other ranges, there is some offset which is caused by this flatness deck issue. And you can see it's like always like 25, or it's 1.1 something something on this meter. Different meters it's can be like, see, 1.2 something something. Sometimes I see like 70 volts on other dead AC boards and stuff like that. So, yep. Okay, we are back. Yeah, you can access, but by readings I was meaning that readings from the scope, not from the meter itself. So yeah, that would be, especially if we could have the oscilloscope like a waveform shown, that would be cool. So let's see, we have the test point that's 401, that should be a low, because I was probing it before. So what we can check first is we can check at the input of the AC voltage input of the AC voltage input, which is essentially what is supplied from A1 board to this A2 board, to rule out that we indeed don't have any signal at the input and amplify it, or however changed from A1 board. And if we have 0 volts from A1 board, then indeed there is no problem with the stuff before it goes to A2. So for that we would need to measure. We have AC in goes to relay K203, which is, I believe, this guy, yes. And then it goes to capacitor C208, I think. Yeah, we don't need this sticker for now. So the capacitor 208 is this huge film capacitor, 220 nanofarads, 400 volts. And it's either, because this is either AC coupling capacitor, or it bypassed and switched to the relay 201, this guy. And then it's routed to relay 202, this guy. And then it goes to the input of, it's not an amplifier, it's the input switching circuitry. So it have different gains, have bunch of transistors in there, and bunch of those small, small floating capacitors and resistors for frequency compensation with different gains. So let's see, we can also check the power supply voltages. I believe we can do that as well. Let's see. So the output of this whole stuff is connected to LT 1057 or maybe 1037 U401B, and here is this 401 U401, which is TL082. So pin 7 is the output, and it's also connected to the attenuation flatness compensation by jumper GM301. And actually I connected this to the wrong point, because there is a TP401, 402 there. That's a better one. And let's probe this GM301. There are 3 jumpers, this one, and that one. So we should see what they are. In the middle left. No, this point is actually not connected to the case. Let's see the GM. What is it? 301. GM301, where you are. GM401. It's been a while since I last time looked at the schematics. Should be somewhere nearby. I see there is one in here. Let's see what that is. Yep, that's the one. So we don't have anything there. Let's see there. Yeah, there is nothing there. Let's try different ranges. I can see a bunch of noise, but there is nothing there. Like no big voltage offset or anything like that. So that is what we should get, I believe. Let's check on the main amplifier input. So this is Q402, this LS591 guy, because it takes the input from low voltage attenuators and a bunch of other stuff with the JFETs, diodes, again a lot of resistance and capacitance things. So we can probe this point, and I believe it's the node that is floated around this Q101, 102, Q103, and yes. So this is this point right here, and we also don't have anything there. Let's try different voltages, I mean different ranges. Yeah, I don't see any huge offset in there, and I can show indeed that it's true on camera. There we are. So the middle line is 0. So I'm probing the point right now and switching through the different ranges. So I can also change the trigger slightly positive and negative. So you can see when I switch, there is a big spike, and then it settles to nothing. So that tells me that the input of the main amplifier is not overloaded. Let's see the output of it. And actually EL2039 is also part in the circuit after this LS591. So we can check inputs of the EL2039 according to schematics, but actually it's THS part in our unit. So let's see that. Okay, so we have some high voltage there. Okay, let's add some measurements. RMS. I believe this probe is also incorrectly set. There we are. So we have plus 7.115 volts or thereabout at the one input, and around the same on the other input. And on the output we we get around 119 millivolts. So essentially nothing. Let's try, yeah, higher voltage, lower voltage. Okay, this is the lowest voltage. This is 100 millivolt AC, 1 volt. Here's the 10 volt range. So we have around 190 millivolts on the output of the amplifier. Let's see another section. Jumper GM403. It's a little bit confusing without the seal screen labels on the jumpers. Let's see. I have actually a circuit board of A2 board without any components, and this is a board designed by people I know, a replica of 3458A A2 board. How cool is that? So essentially, if I would get all the expensive parts, I could make our own A2 board. But what matters is that all the labels for jumpers are here, so I can just use it as a reference. Okay. White wire. No, that white wire on the AC board is actually a capacitor. There was a question on the chat. What is the business with this white coiled wire hanging around? This is a small couple picofarad capacitor made from Teflon coaxial wire. As you can see, it's going on that sensitive node, and there for that AD711. So that's a capacitor. I wish I could shadow it somehow. There you are. So it's a just coiled length of coaxial wire of specific dimensions to get a super stable capacitor. So let's probe the output of the amplifier. That goes to the overload detector and level trigger. That is GM403. So I can see GM403 right there. Okay, we have same 100 millivolts. Let's go to the different range. Okay, Let's see, GM401, which goes to the RMS converter. GM401. And they are all coming from the same point, so what we can do is also check the flatness attenuation flatness compensation output. I think I know why I didn't see any voltage on that 401, because it's the current deck, it's not the voltage deck. So of course the current would be the voltage would be zero there. Let's see. We can check the supply on the amplifier next to it, just to make sure. It should be plus 14 volts and minus 17 volts. And let's see, pin number 4. Okay. So we have minus 17.7, good enough for America. And the positive should be 14 volts on the pin 7. Yep, we have DC plus 14.1. And pin number 6, it's around 0. Pin number 1, 0, around 0. Okay. And we can check the pin number 1 of this deck, which is reference output. Let's see, it's U301. U301. Okay, there it is. Should be 7240, and it is 7240. There is should be minus 1.4 volts at pin number 3. Yeah, we get to minus 1.15. Okay. Let's see some of the digital signals. Pin number 4. Change some ranges. Okay, we see some life there. Pin number 5. Pin number 6. This is a deck that is used for attenuator flatness compensation. So I'm just checking if all the control signals are changing and alive, which they are. There is something getting hot here, slightly hot. Ouch. This amplifier is indeed very hot. I'm touching it with a finger carefully, and it's like maybe like 50 C. It's not scorching hot, but it's definitely unhappy. But it could be running that hot because its supply voltages are plus 14 minus 17, so that's a large voltage swing. So what we can do is let me show the idea. I have in here. What else we have? What options other than that? There are also a bunch of DG211 switches, but somehow I suspect it's not the problem with them. We can also check another deck, which is supplied by -10 plus 5 volts. It's U406. Let me see, 406, I think, yes. And I see it in there. So pin number 4 is -10. That is correct. Pin number 17 is +5. So pin number 17. That is indeed +5. And the output is pin number 2 is around 0. Okay. And then there is a buffer. Let's see. You can also run the ACAL AC voltage just to see what happens when we run the failing test. Okay, bunch of signals. You can change the time scale a little. ACAL, AC. Okay, ACAL, AC, enter. So we have this kind of interesting stuff. That is at the output of our amplifier. Let's see what's at the input. Should be around 7 volts there. Yep. Okay, there is nothing. Interesting. I expected something there. Let's see before the MOSFET. Okay, there is some small signal there. I'll call AC. Okay, so we see that funky signal again. That comes into the main amplifier input. Let's see the output. That would be a tricky one to find, or not. DG211 U403 pin 3, 403 pin 3, there we are, local, AC, okay, we have the signal there. Let's see pin 1, 0, let's see pin 8, okay, okay, this is some high voltage there. Okay, so that's plus 5 volts. And the output would be pin number 2. Yeah, I see some signal there. I can turn off the cursors. We don't need them. See some signal there. Let's see pin 7. I'm just checking the DG411 switch. And let's see another one. This one should be closed. So actually this should be open. The previous two were closed. Signal at the input, no signal at the output. And there's some small stuff, but I think that's fine. There should be one more switch, but maybe it's unused. Okay, so the switches are working. In such cases, it would be nice and helpful to have another meter open, so we can compare the signals. Should we do that? Otherwise, this live stream might be stuck for 10 hours. And the scope runs, I believe, Windows 7? Or, yeah, this should be Windows 7. Yep, there you have it. Q801, 802. What is 801, 802? I'm trying to find Q801. I see a bunch of Q9 something. 900 something. I don't see anything Q800. So let me show Input routing, flatness call steps. Okay, yeah, I can find that. Let's see. Where is it on their circuitry? Should be somewhere near. Okay, Q900. It's on the right on the top. Let's see those. So we can see there is Q801 DG211, which is the switch from DC board. Switches bunch of stuff to the calibration input for K201 relay. 203. So we can check that output of that mux. Q801B, pin number 6. Q801B, pin number 6. I believe here it is. So let's do a AC again. So we have the signal there. Looks fairly decent. I can do it again. So that is the signal at the output of the mux that fed into the input switching relays. So I think the calibration circuitry that generates flatness is working. We can also check on this cap, the same thing, to check that the relay is working. Yep. And we can check the GM301. We see nothing there because it should be current. And we can check the mux from the input high voltage attenuators. Should be DG211 pin number 3. DG201, sorry. Pin number 3. Yeah, we have very small signal there. Let's see that the control is correct. So 5 volts. Okay. Five, 499. Okay. 11. This switch is fine. Yeah. Let's see what else. We can check minus 18 volts, or is it minus 10? R413, R413. Let's see where you are. C412. R413, there you are. Yeah, minus 18 is there, so no problems with the power anywhere. Let's see what else we have comments on. Well, the fuses are fine here, so it's not the fuses. Flatness duck. And the issue is on 10 volts, so at least that's the one that it fails first. There is the amp offset circuitry around, so we can check that. Maybe it will give us some clues. U402 should be small amplifier. U402. There it is, LM358, the most jelly bean possible op amp. And we have 5.45 volts on the output of it. So that's pretty big for the offset. And if I run ACAL-AC, it doesn't change. Pin number 2 is nearly 0. Pin number 3 also nearly 0, but pin number 1 is 5.4 volts. And that is fed into the RFBA and also fed through some resistors to output of our precision amplifier. Let's see RFB B, which is another part of this op amp. It says 8 megahertz compensation. Pin number 7. It's 2.1 volt. Okay. And it changes to 2 volts. If I start ACAL-AC and goes back to 2.1. And this is the stuff around U406, AD7520. Interesting. Interesting. What we can do is we can remove this op amp, removing this compensation stuff, essentially run without it, see what happens. So the part I was talking about is right in here, this op amp. We can just snip it out, probably. Let's see if I have a replacement just in case. Op amps and comparators. I also, at this point, very tempted to take apart my second, actually third unit, and see if we can compare the signals, because that should be much faster. And I actually wanted to do a couple other things to that unit anyway, so we could hopefully progress this repair, because it's kind of getting somewhat unexciting. So let's see, I need 358, the most jelly bean op amp possible. $319. There we have. Well, this is actually a fancy one. It's the hermetic version of it. So probably we don't want to use this one. It's cost like $40 or something like that. I'm sure I can snatch it somewhere else. Well, that's not much isolation. The little amplifier board from the Fem2Amp unit have much more of that. Let me show you just in a sec. This little guy. You can see all the slots around it. If I have the flashlight, then I could shine some through. There we are. Damn it. all those holes between the pins. So there we are. Let's take it the third unit apart and go from there. Well, the holes are easy. Try to drill the slot between the SOIC pins. So that one is more fun to do. All right. We had one broken meter, now we will have two broken meters. So a bunch of stuff. Whoops. Need to remove the GPIB cable and off we go. This one actually also no fan. Okay, now I see. I believe the fan in this unit died because it's quite hard to turn. Let's see. Now it's barely turning. Okay, no wonder it had reporting high temperatures, so we'll need to probably move it around a little and find a spot. Let's turn this one off. I need to remove the bottom cover. The easiest thing we can do is to swap the whole A2 board and test if we have any other issue with this meter. Probably will be more exciting, and then we can compare the signals between the two. I don't know what's the deal with the writing on the cover. So also, you can see this meter is not quite standard unit. And why is that? Because it has a shield here. Standard unit No shield. Special XDevs unit, shield. Magic. Wow, this is hot, like super hot. That fan needs definitely a replacement. Yeah, probably would help if I remove the switch first. There we are. Come on. You can see this is actually an older board. This board dated from 1989 and 1989. Have the same capacitor made from the coax, and you can see it also doesn't have any drill holes around the Teflon. Have bunch of darked spots in the hot component placements. Some bodge wired capacitor resistor. So let's put it in and see if it chooses. What's there? So you can see actually the pins that connect this board to the A1 board under it, and also this is the power from the power supply. Alright, there we are. Also, it's important to fasten all these mount holes, because they actually carry not just mechanical purpose but a functional as well, because they connect different ground points on the A2 board to the common point of the whole isolated frame, which is connected to the LO guard. We don't need to connect this push rod for now. Let's see if it works. All right. We can check if we have that voltage offset on AC voltage. Let's go to the... We had 22 volts before, and now we have 94. It's even better now. Well, better in the... not as really better. Let's actually run the self-test to see if that gets cleared away. Or maybe we killed another board. I don't know. Okay, so here it usually failed. Doesn't look like it's failing now, or maybe it was failing later. No, I think it's fine, because the next test is DCI, and then it's done. ACI, yep. Okay, passes with this board. But what's the deal with the 90 volts? Is it because the constants are all busted up? Let's do AKL, AC. That's an interesting... So it's running for now. Let's see if it passes. So the other meter I have, this is like a test unit that I just do some experiments with, do some tests. It's not a special unit, other than having shields in it. It's a standard hardware. Have the new front panel and have the keysight label, but it's actually HP unit. So still running. No flames yet. As for the fan, actually that fan was already replaced, and that was I installed a slower fan to see how affects, like how the stability and temperature coefficient of the meter is affected by the hotter temperatures and slower fan. Usually, like my two other meters that are right over there, hiding in the dark, those using faster fans than standard. So yeah, AKL passed while I was distracted with stuff. ACAL AC passed, and now it's showing 0 point something volts on kilovolt range. Looking good. Lower range looking good. Also looking good. Looking good. And yeah, no problem with AC with this board. So what we can do now is we can put the bad board in a good unit and see if all the issues will be happening there as well. Because it doesn't really matter on which unit we will be fixing the board if the board causing all the same issues. So let's do that. So now I need to find the power cord, and we can see if that meter fails the same way. There we are. So let's see AC voltage. So we have, yay, 74 volts offset. Let's do the self-test. Self-test failed. I bet it's still hardware failure flatness duck convergence. And same error. Okay. So now we can do some compared measurements using the old but working board. I think most of the viewers already probably fallen asleep at this point anyway. Whoop. So I don't see how this could be any exciting. Let me put this screw so I don't forget it. Also, this is a little bit interesting board. You can see you have Atlantic on the socket. How cool is that? All the HP part numbers. The glorious capacitor. Even have the ceramic RMS converter. Alrighty. Who added the socket? I don't know. So let's see those signals, shall we? We can just check ACL-AC. That same signal from AC calibration circuitry to confirm that it's all fine. Pin number 6. Yep, signal looks the same, but it runs for longer because obviously it doesn't fail at the first point. So I'm fairly confident that this flatness calibration circuitry works fine with Q801, 802. We can rule that out. Let's see the input amplifier. This battery will die too. There we are. Back in business. What's the failing step? The failing step is the first AC, ACAL AC DC 10 volts, I believe. M511, what is that? M5. Oh, you mean the input Q402? I see the input on it and I see the output, so I was thinking it's okay, but we can check with this working unit to see if the signals are same or not. And let's see. 10 millivolts. Well, probably then 10 millivolts, yes. I can run again, and we can see that it's the same issue. ACAL AC, enter, ratio 1, fail. So it's not even that. So let's see what on the ratio 1 test when we do the ACAL AC with a good board. So I can put the to that M5911. This is probing pin number 3. Input from all that attenuators for low voltage. Let's see, ACAL AC, enter. We have little faint voltage there. Should get bigger. Let's see. Little faint voltage again. Different frequencies, faint voltages. Let's see, let's keep it going. I expect it should get a little bit larger and larger as the time test progresses. This is 1 volt, next should be 10 volt. Actually, voltage is also quite low. Like this is 70 millivolts per division. And this is again input of the amp in of main amplifier. I did see the same signal on the failed board, so that is okay. That means that all the input attenuators most likely fine. Let's see. Right now it's nothing. Testing probably something else, and test is done. So let's see the output of this, not the output but the second node. Pin number 3 DG20211, it's U403. This is the next guy, pin number 3. There we go. Call AC, enter. So we have a bunch of pulses. This is a differential amplifier, so it should be the same. Okay. Looks okay. We can see the output of this stuff, output from Atlantic. I believe it's pin number hard to see. Should be 1, 2, 3, 4, 5, 6, 7, 8. 8 maybe? Yeah, it's 8. We have a big signal. It's a very big signal. So there we have 20 milliseconds per division, a bunch of alternating square waves. This is the output of the Atlantic 2039 on the good board. So small signal. This is 100 volt. Still going. And this is 1 kilovolt, big signal, and 10 millivolt. So I'm jumping around, and it's done. So let's see that comparator that I was checking before, and I seen 5 volt something something. Pin number 1 here. And here I see a really big voltage. No. 4.9 volts. Okay. Let's do a cal again. Enter. Nothing. Just fixed 4.86. Let's see pin number 7. Around 2 volts, so the voltage is about the same. Let's keep looking. 4.9. We can check that attenuation flatness deck. GM301 is there. 20 millivolts something. Let's see. Non-inverting input of U401. Pin number 5. Oop. Yeah, there is nothing there. Let's probe the stuff on the bedboard. So if you have signal at the output of the main amp, you should follow the signal at the EL2018 comparator. Yeah, we can do that. But this is actually this board have replaced input amplifier and EL2018 with the newer one, and I didn't ever hear that anybody had the issue with the newer parts in terms of comparator diodes and stuff like that. So I'm not convinced it's the comparator issues. So let's see this is the auto call AC. So this is the amplifier output on the new board. So we have a signal, but it's small. Okay. Let's run again. Signal there, and I see it's not stable in amplitude. It's kind of all over the point. Let's see here again. Yeah, here it's more stable, I believe. We can do the test again. Probably I can switch the slower speed, so we can capture the whole sequence. Do the single capture. Single. Channel 3, let's go. Single. Okay. AC. Okay. So that's what happens. It fails like less than a second. Let me zoom in. So this is 500 milliseconds per division. Let's zoom in here. And that's the signal we got. We can see the first, maybe. So I'm not sure if it should be wonky like that. We can check with the good unit now. Yeah, and then you have the signal right in there. Let's see the good stuff. So I'll just probe now to the same point. Again, this is the output of the comparator. Same scope settings. Single. Cal AC. Enter. Okay, so this is how it looks on the good unit. So I would say it's fairly close. Also wonky a little bit. It's close, but not quite the same, because let's see. Here we have the first of all much faster edges. Well, we can check the 1218 as well. Level detector. Let's do the reset. I can check the output to check that what's supposed to be there. Pin number 7. 1, 2, 3, 4, 5, 6, 7. Let's run ACAL-AC and probably change some settings in the scope. And run. Okay, and there is, whoa, there is that signal always there. Enter. This is level trigger output. Let's see the pin number 2. Almost nothing there. Pin number 3. Some small sine wave. And this is the ACAL stuff. And the output is pin number 7. Bunch of square waves. I believe these are square waves. Yep. And we can see the overload, just to be sure. Where is it? 5. Okay, it's whoa. It's over there. No overload on plus. It's hard to reach there. There, no overload on minus. 5 volts constant. And 505. Where is the U505? There it is. Pin number 3. That's the input for the overload circuitry. Whoops, I think that was me. We can see now, also test on the new board. Same stuff. Whoop. So the question chip that on that page board. So the output of the comparator is level pin 7. There we are, and nothing there. Okay. And some square waves there, and then it's gone. Pin number 2. Some signal, and it's gone. Pin number 3. Some big square waves. Let's see the overload. So pin number 1 is the output. So we still have that 5 volt something. AC doesn't change. And pin number 7, 5 volt something. Doesn't change. So it's not the overload, and I believe it's not the level trigger. And pin number 3 is the input for the overload. Yep. Okay, let's see something else. What's the input to the RMS converter? And check the power for it. So should be pin 10 and pin 11. Okay. Pin 10 minus 15, pin 11 plus 15. Okay, on the bedboard. Fine. also fine. Now let's see the input, pin 13. Pin 13. We have some squiggly lines. Let's see the bad unit. Okay. TP601. I want to see the TP601. Where is it? TP601, where you are? Where is it connected to? U504. Who is U504? That's the LM6321 buffer. Let's check that. Pin 7 output. What? We got the problem here now? Oh yeah, of course we got. I think I might need a break. So that's the output of the buffer. And the input is pin 2. Okay, buffer works. Maybe it's the trigger level deck. Let's check those. U001. Where is U001? There it is. Pin 1 and pin 7. Nothing there. And nothing there. Pin 2 and pin 6. Okay. Okay. Nothing there. And nothing there. That's the same. Okay. We can check again Q302, U302, pin 6. Okay, nobody there. Small signal there. I think we can just connect the AC signal from the generator and actually see what's going on instead of trying to run the ACAL every time. And there is some signal there. Let's do that. So I think we can just use that guy there. So we can use maybe like 1 kilohertz, 1 volt. megahertz, 1 volt. Cable connected right there. And I'll enable the output now. Okay. Output enabled and disabled. So we have voltage goes up a little bit on the readings, but that's completely incorrect. And I think I would need actually one more cable so we can connect the same signal to both units, and then we can just probe around and compare. And it's raining hard outside, so it's fun. At least it wouldn't be hot. So hopefully I can get the lab temperature back to normal. There we are. I'm back with the cables. Little box with little somethings. Actually, I think it's better if I connect on the rear, so it's not in the way. Adapters with adapters and adapters. What can go wrong? So we have signal connected. Actually, I also want to have it connected to the scope on the separate channel. Should we do that? Yeah, why not? Okay. Set channel 2, no attenuation, Fluke division. There we go. There is our signal. And we can probe around. So the sign line is the signal connected to both 3458As, and the purple is our probe. So let's go through all the input circuitries and see what we get in where. So on a good board, we can check at the input amplifier. There is our something. Well, it's really small because we are on. Okay. There we have 1 volt range. So signal looks good. Signal looks good. And let's see what goes to the. Here we have huge signal. (200 millivolts). This is TP401 point from the main amplifier output. And the level trigger from that EL2018 should be here, so it looks good. So we should expect to see about the same from the bed unit. Let's see. Signal is the same. But problem. Okay, there is no level trigger. Okay, that is interesting. to say at least. Let's see again. This is signal. Sorry, output of the amplifier. Looking good. Let's see what goes to the buffer input. Pin number 2 goes our signal, and the buffer output pin number 7 output, looking good. Then comparator for overload, pin number 3 of 505. Here's the comparator overload input, pin number 1 output, stuck high, and pin number 7 also stuck high. Okay, no overload. So as there is a switch DG211, that switch is actually, there are a lot of them, before we go to EL 2018. So let's see, input of the 2018 EL chip, that's pin number 3, 1, 2, 3, nothing there, that's not right. Pin number 2, also nothing there. Let's again check with the CUD board. Pin number 2, something very small there. Pin number 3, there is a signal. So, okay, this is a different behavior. Let us check the output of the buffer. Input pin number 2, yes. Pin number 7, yes, same. So there are a bunch of switches. So I think we can just replace those switches, and instead of checking all of them, I think it will be faster. Let's do that. Anybody still alive? So what we see, what the behavior is different. The things are different are we get the good signal out of the amplifier here, good signal out of the buffer, this chip here, but we don't get signal to the trigger level detection circuitry, which is this patch board. So there are two switches, DG211, I think this one and this one, that do the different switching and stuff like that before the signal reaches there. So let's take this board up, away and replace those two. And on the circuit, whoa, not so fast. On the schematics, the stuff affected is, let me focus, come on, there. So I can show so this is hard to see, but that's the idea essentially. We have the good signal that come in here. This is buffer, and this is switch 1, switch 2, 3, 4, 5, 6, 7, 8, and then this is the comparator that do the detection for the level, and then this is the output for the level trigger. So we don't have signal here, we don't have signal here, we don't have signal here. So something in this area is bad, and the only thing here are switches, and the comparator is fine. So probably maybe one of these is bad. Let's see if the theory holds true. And we can do something else, like soldering. But first, we need to remove the board. Wiggle, wiggle, yeah. So one way is to remove them is, so this is this one, 503 and 502, yep, these two guys. So one way is to remove them is use the heat gun, and that would ruin the board. And another way is to desolder each pin, and that would be tedious and long. So what I like to do is to chop, chop, chop. Let's do. Now it still requires some careful snipping action, but here we have a lot of room around the parts, so we just snip, 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 snip. Also, it's important to use sharp cutters, otherwise you will jam the pins and they will be still kind of connected, so it would be less fun. Bye bye, Chippy. So I love this RM TX 576TX. These are tungsten carbide jaws, so they will last forever doing this kind of stuff. So let's continue. Snip, snip, snip. Easy peasy, and off we go. Now you would say like, okay, now you have all these pins sticking out, what you do with them? Well, I'm glad you asked. What we do with them, we just use our good old tweezer and good old ERSA icon soldering iron and get them out. This is also helpful because it minimizes the heat to the board, because as you can see it takes just less than a second for pin to heat up because it doesn't have all this thermal mass from the chip, and you don't risk into damaging the sensitive boards, especially multi-layer ones. But this is of course if you have the deep packages and a lot of room like here. With the modern electronics, it's usually like all the leadless packages like QFN, BGAs and other crap like that. So that's why I like to work on the older equipment and older test measurement equipment, because it's like fun to service. There we go. So now we need to clean up the holes for the new chippy, and then we can put the new chips and see what happens. So for that I'll need to, probably I'll do this first. This is a toothpick, so it have the perfect size for the deep hole. So I can just heat up the point and then press the toothpick through the hole, so all the excessive solder will be jammed on the bottom side of the board, and usually I have enough space to put a chip, even not cleaning the bottom. And then when you solder from the bottom, you have all that excessive solder to flow back into the pin and make a good joint. And it's also quick and easy, and you don't make a mess with the flux everywhere. That will be hard to clean afterwards. Okay. Now the second one. Also one could say like, oh okay, like instead of cutting these chips out and hoping that issue was in one of them, you could test each of them and find out which actually chip is dead. Well, yeah, sure, we could do that, spend another couple hours, but like these DG211 switches, they are fairly cheap, like a few dollars a piece, So it's just not worth the time to spend all that effort just for sake of saving like $4 when we're talking about repair of the instrument that costs 10,000. Like, yeah, come on. Okay. So now I'll move a board a little bit further here with my microscope set up and the fume extractor. And there is the microscope and there is the fume extractor. So there's a lot of light there. I'll just inspect that there is no problems with the pins and joints and stuff like that. And there were questions about the cutters. Well, they are not all full carbide. They are like the jaws itself, they are carbide, but they actually welded to the rest of the body is the steel. So you can actually see like the different colors. And brand new, they are around $200, like 220 or something. I bought them second-hand, used for around 100 something. So, but like I was tired of replacing the busted cutters every like half year. So I just bought these ones and I love them. They also have a very nice clean cut. So just very satisfying to use them. Of course, there is a problem with the carbide jaws that they are very brittle. So if you try to cut something hard, like I don't know, stainless steel stuff, then you will break them. So don't try to cut the hard stuff. But for copper pins, like component pins, wires, like we use small electronic stuff work. They are perfect. Okay, so everything looks fine. I have just a couple touches here and there. Now I'll clean a little bit. Oh. This is the 99% IPA. Nothing special or fancy. Let's see on the back. Yeah, looks okay. I see there is actually another. One of the chips was replaced before, all the solder marks. And here, so somebody in here, somebody definitely worked on this board before, replaced a bunch of stuff, but probably not the right stuff. So let's put the new switches in and see if it helps. Again, I don't have 221s. I mean, I have them, but I don't know where. So it's just, I'll use fancier ADG 441. They are supposed to be a better replacement. More expensive too. So, fancy schmancy. I also bend the legs a little inwards so they are easier to get in. Let's see, make sure the orientation is correct. We don't want to put the chip backwards. That would not be fun. So let's see. Some more. There we go. Second one. This one went somewhat crooked. So, okay, I see. I think it's good enough. Also, some crazy people using huge temperatures for soldering, like, I don't know, like 500 Fahrenheit, 400 degrees Celsius. Like, that is ruining the boards and components. I use usually 280 centigrade, whatever that is in Fahrenheit, I don't know. So don't overcook your board. If you feel like you don't have enough temperature, well, that's not because of the temperature, but because of the soldering heat, and have no way to build up fast enough. So you need either better thermal contact, meaning either bigger, juicier soldering tips, or the direct heat soldering irons. Or you have bad contact, thermal contact with the joint you're trying to solve. Like for example, if you like soldering on corroded pin, then you'll have like barely few points of solder touching it. So you don't have the thermal transfer to heat up the board and the pin to the necessary temperature. So while your soldering tip is like scorching hot, the actual joint is cold. So use the proper temperature, folks, and proper tools. Because the good rework is the one that you don't see. Should be looking the same way as it was soldered on the factory, using the ovens and all that. So that should be the goal. Okay, both chips are installed. Let's clean up the flux, inspect our work, and put the board back in and see what happens. All the resistors nearby, everything else looking pretty good. I don't see any other bad issues. At least visually. To clean, I just use the Q-tip and scrub it angrily around all the pins till I don't see any residue. So sometimes that takes like a couple iterations. Whoops. It's not perfect, but I think it's good enough for now. So we can do some tests. Let's do it. Where is our meter? There it is. There we are. Let's put all the screws back in. Whoops. And last one. Okay. Let's turn it on and see what happens. Now we just need there we go. Let's the fire emerge. Okay, that's already looking promising, but not quite. Let's see, go. We have our 74 volts. We have our 1 volt or thereabout on AC. Let's do the self-test. And let's disable the source first, just to make sure. Test. Of course, according to Murphy law, it should still fail, but never know. Yep, still failed. Okay, it's not the switches, I think. Let's see the error. Same stuff. Well, that was a good try. Let's do AKL AC. Yep, that was not the switch. Oh well. Let's see again what happens with the signals. Let me move this over here so you can kind of see the scope and what I'm probing at, like so. Was a good try. We have 1 volt. It's funny how they all match almost the same. So let's continue. Let's see. Output of our buffer. Big juicy signal. Output of our buffer here, same big juicy signal. Then input, let's see, line frequency, pin number 2 of 503. Pin number 2. Okay, that does look like a line frequency maybe, because it's 60 Hertz. Let's see in here. Yeah, looks the same. Line frequency is there. Let us see the pin number 3 of the EL 2018. Okay, we have this like 20 millivolts AC signal that is in sync with our input signal. And here, pin number 3. Hold on a second. That is weird. Okay. We don't have a signal. So, what else is connected to this pin number 3? We have 2 switches before it. We have some transistor that switches this stuff to ground. It looks like. Maybe. Let's see what's in the input of that. And that transistor is driven by reg 13, which is one of the shift registers. Let's see what's on the input of the transistor and where it is. It's Q501. It's this bastard here. Let's find what's the good stuff. Okay, C510. We have AC signal there. And then on the other end we have something big. 1.474 volts with the squiggly line. Okay, what do we have here? We have dead line there and dead line there. Okay, and that's pin number 1, pin number 2, pin number 3. Okay. Okay. That looks not quite the same. Okay. Let's see pin number 2. Okay, there is super small signal. on the pin number 2. Let's see what's in here. Or was it, yeah, that pin number 2? Nothing there. Something here, nothing there. Okay, let's check that R502. Should be there. Small signal. That should be big signal. Or not. Oh. So let's see. Trig V is generated by somebody else. We already was looking there before. Here, trigger level select. It's 358, which we was looking U001B. I believe it was somewhere here. U001 pin 7. There. I think I need AC coupling on this signal. Vertical setup, channel 2, channel 3, AC coupling. No? Am I probing the right pin? Pin 7, yes. Pin 6. Pin 5. Okay, hold on a second. Oh, right. Pin 2. Yeah, that is correct. I believe pin 7. It's because this big signal is coupled back. Okay. Pin 3. So let's find out why we don't get the signal on pin 3. Let's see which switch is pin 11 502. 8, 9, 10, 11. Signal is there. Pin 8. Here. Whoop. Pin 8. That should be pin 6. Yep. So we have signal there. Pin 6. We have very super small signal. So pin 7. Super small signal. Pin 10. Some dodgy signal there. Let's see, pin 15. Some still dodgy signal there. Pin 14 of 503. Okay. Yeah, big signal there. Okay. DCV pin 15. Nothing there. Big signal there, and this one is we need DC coupling, I believe. There. Maybe the controls for the switches are not good. Those shift registers. Why? Let's compare that. This probe should be 10. Gain attenuation 10. There. Oh, wrong one. My bad. 10. This one is 1. There. Okay. So let's see, each switch +5, 0, +5, +5. Let's see here. +5, 0, 0, 0. Okay. So the control is different. Let's check again. 5, 0, 5, 5. Let's see here. 5, 0, 0, 5. Now let's see here. 5, 0, 5. What is this? Okay. That doesn't look right. Should be 5. But here we have small sine wave. That definitely doesn't look right. And controllers that switch this rack 57, 56, 53, 52, 60. These are all two of the U013, U004 shift registers. 004 and 013. Where they are. 004 here, 013 there. It's a MC14094 BC, and in there it's the same chip. It's 4094 shift register, and actually I do have a couple of them, I believe. Yes, CD4094. So they are powered by, let's see what they are powered by. Could be that we have dead switches, dead shift registers. I don't know. But I guess 2 more chips to snip. Let's find out. We can see what happens when we run AutoCal, if those pins toggle at all, especially this dodgy one. Yeah, there is something strange there. Let's see on the good unit. Doesn't switch. it just stays at 5 volts, so the level is different, and also there was that sine wave leakage. That's interesting. And of course, like if the control is all bad for these switches, then the switches, even the ones that we snipped out, maybe they were good, but then they will be configured in their own state, and that would cause all the issues. So yeah, let me double check real quick that I have the CD4094, and that they should be the same as MC14094. Just double confirm that the voltages and everything else is fine. All right. So MC14094, I remember those failed a lot in Keithley 2001s that I was fixing back a couple years ago. So yeah, that's not like uncommon. So MC14094 is 8 stage shift store register, 3 state outputs, capable driven TTL loads, DC supply voltage up to 18 volts. What's the logic truth table? And the CD4094, it's from Texas Instruments. Voltage up to 20 volts. Let's see that truth table is all the same, because that is kind of important. Q7, no change. Yeah, it all looks the same. So I think we'll be fine. So the CD4094 switches data setup time, strobe pulse. Let's see how fast they are. Their propagation delay. Around the worst one is around 840 nanoseconds, and let's see the MC one. Yeah, around the same, 840 nanoseconds. I think they are the same, just different vendors. Well, let's go snip snip. Snip, snip. So the chances are that the switches are bad. The thing that I didn't like is that these are digital input and output chips. There should not be like small sine waves and stuff like that happening at the multiplexer input. So multiplexer control input. There should be either 0, which means the switch is closed, or 5 volts, which is switch is open. Not some strange analogy stuff. That doesn't make any sense. Should we replace just one first? The one that controls most of them? Well, yeah, let's swap just one that have the last one in the chain. It's U004. and it's right under this funky looking capacitor cable, so we'll have to get it out of the way and have all the picofarads fly away, but I need access to that area. We have to recalibrate everything anyway, so it's not that it matters much. Oh, actually original chip is also CD4094 here. Okay, so we're replacing the same part to the same part. Even better. I wouldn't bother changing the lens and all that, because the process is exactly the same. Come on. It was always strange, and I'm not quite follow why like chips like that, like in the middle of the instrument, far from the like possible high voltage input overloads and stuff like that, would fail. But given that, like, I don't know, like how long this board is designed and made, not designed, made in 2000, so it's 21-year-old board. Maybe just because the processes like with semiconductor process or something else was affecting the chip, and after 21 years it failed just randomly. So it's like in many equipment I seen like these cases when like in the middle of nowhere some digital chip has failed or like memory failed. I would understand that for like stuff like flash, because you can like have too many cycles on it and then you burn a hole in the memory cell, doesn't store anymore. But logic chips, especially like low power stuff like shift register in here, it's not like we have billions of transistors like in a modern CPU or FPGA. Maybe somebody who knows better about chip designs and stuff like that can leave in the comments like what is the typical failure reason for small signal chips, other than of course like manufacturing defects, stuff like that, because it's not like this chip died early when it was made. It's obviously worked for many years. Putting the new chip in. Maybe there was some issue with the original switch, and then the switch got like analog signal go through the digital control input of the switch, and then killed this control shift register. I don't know. That's kind of far-fetched theory. Okay, let's try. So I've replaced U004, which controls, let's see, reg 57 till reg 64. So it controls U503, 503, 502D, and I believe 502, 502C and B. Oops. Let's put it back. Okay, put the screws in. Now, of course, if the previous, like all these shift registers, there are like whole 8 of them. So we replaced the last one in the chain, but they all connected in a long chain. So first, like they shifted register 1 and so on and so on and so on. So if any of the switches in the previous chain failed, then all the following ones will fail. Well, fail mean get the wrong data to latch their outputs and inputs, only outputs actually, and will get the incorrect outputs on their pins. So maybe it's one of the previous ones that is bad. So if this time fails too, then we can actually go ahead and see the data that's sending between the switches to see if there are some changes and stuff like that. Alright, let's turn it on and see if we get the right signals this time or not. Yeah, I think you can see the scope right there. Okay, everything's screwed in, connectors in place, power on. Let's see if we have crazy voltage on 1 kilovolt range. Yeah, we still have 74 volts. Let's see, we'll go back to our 1 volt range. Let's probe some signals. So let's check. We can do the reset actually. And preset, just to make sure we have all the same settings between the meters. Preset norm, AC voltage, and trigger auto, and go to the 1 volt range. So we can do the same here. Preset norm, enter, AC voltage, trigger auto, enter, and 1 volt there. So these meters should have both same signals, same everything. Let's see. So inputs or control inputs of 502 switch. We have +5, 0, +5, and +5. Let's see here. +5, 0, +5, +5. Okay. Let's see here. Second switch, U503. First input 5, 0, 0, 5. Let's see here. We have 0. That is not the same. 0, 5, 5. It's closer, but not the same. Let's see the self-test. So the two incorrect pins, but we don't have the sine wave anymore, so that's a good sign, I think. Yeah, it's just 5, 5, 5, and 0. Five, 0, 0, 5. So we have two pins, pin number 9 and pin number 16 of 503 are incorrect. Beeped, self-test failed. Let's see the error. Same error. Call AC. Same error. Okay, so who is driving 503? Pin number 9 and pin number 16. Pin number, okay, pin number 9. They are controlled from the hard to see register. Well, one is definitely previous register, the pin number 9, or pin number, yeah, should be 9. Is it? No. 58 and something else. Let me open the electronic schematics. Man, this repair, I was hoping it would be 5 minutes. Put the cable down like the signal path does, and skip all the boring part, and that's it. Repair done. But we're doing real repairs here. So okay, pin number 9 is register 56, and pin number 8 is register 53, and 58. So I guess we need to replace the last one, the one before last. I can show probably in OBS. Not this one, this one. Whoa. So this is what we're talking about. These two registers are, so I replaced this last one in the chain, but we still have register 56 and register 53 control from this U013. So let's, and they all go to right, where is it? Here. So this is register 53 here, and 56. Pin number 8 and pin number 9. Okay, let's see the stuff again. Pin number 8 should be 0 volts. Pin number 9 also 0 volts. Here we have 0 volts, and we have 5 volts. Uh, 013, it's the next one on top of that. Wiggle, wiggle, yeah. I need to fetch another shift register before I snip the old one. Where's my drawer with the registers? There we are. I think I need to just sniff around. almost there. Okay, clean up a little. Too bad I don't have the microscope camera to show the small reworks like this. Would be cool to have someday. Yeah, I think it's good. Let's put the new chip in. Oops. Okay. This is interesting. Yeah, this will not work. I was trying to put the CD4069 in the place of CD4094. That's close, but not quite the same chip. I was wondering why there was extra legs in the PCB the chip didn't have. Okay. So the question remains, we need to find the C4094. Where are these small buggers? I've just seen the whole box of them. These are Zeners. $40.94 in SOIC package. Not quite what we want. Okay. There we are. Little buggers. Whoop, where is the camera? Do 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 do. Come on out now. There we go, ski. Get in. Okay, chip is in. Let's clean it up. Well, let's see if anything changes. Okay. Let's turn it on and see what happens. Let's do the same settings. Reset, norm, AC voltage 1 volt, and trigger auto. There we have 1 volt. Let's check the levels. So we should have 5005. Let's see on the good one. 5005. On the bad one, 0 0 5 5. Still incorrect. Okay. Let's do the self-test, or we can just auto call AC. Yeah, okay. That's a disappointment. Let's see what's before switch pin number what? Okay, nobody there. Okay, there is something there. I think we need faster trigger. Whoa. So that was the output of the 13. No, that's the input of 13. Let's see the output. Oh, wait. Okay. There's some life in there. Doesn't depend on range. That doesn't depend on range either. Okay. Let's see some life in here, if there is any. Whoa. So the data is being sent. Let's see the signals. No signal there. What else can it be? Why the levels are incorrect? 503 1 that is 5 8 is 0 that is 0 and that is 5. Okay. So the three levels are different. This is line frequency switch. this one is triggering switch, and that is okay. But why? What else is connected to them? I don't think anything else is connected. Oh wow, that doesn't work at all. Synchronous AC voltage measurement. Well, no wonder, because the trigger is not generating anything. Oh, okay, there is signal there now. Now we have trigger, okay. Okay, this switch is correct now. And that switch is correct now in this mode. Okay. That's interesting. So in synchronous mode, we have, I believe, the right levels. Let's see. Some signal there, some signal on the trigger, and some signal there, some signal on the trigger. But the voltage is wrong. So okay. Let's see what's on the output of the amplifier. There is a signal. Amplified and attenuated as expected. And after buffer, everything fine. So in synchronous mode, it should go a few different areas. So it's either go to RMS converter and to AD high speed, and that is, where is it? Switch 903 15. Switch 903. Where is it? There. Nine oh three pin 15. I don't think we can run for much longer because I'm running out of the batteries. And also sensitive boards and glove care, well, dead boards are not sensitive boards, they are dead boards. So that rule doesn't apply there. And humidity in here is about 45–50% now, so there is no much ESD chance. Let's see if I can move, so it's a little bit better to see where I'm poking at. All right, where we were. Wanted to check what's coming out of the RMS converter. So we need to see what's in there. 1.9 volts. And switch it out to minus 13 volts. And there is 901. So interesting. To A to D we get minus 13 from this guy. Switch number 10, switch number 11. So this track and hold stuff. Switch it off. Okay. How about 902? Where is it? It's this guy. Pin number 3. Our magical switched capacitor. It's actually 100 picofarad. And pin number 2 and pin number 6. Okay. Pin number 10. What is this nonsense? What's going on? Whoa. That's interesting. Is this in sync mode? Yes, it is. So in sync mode, ADC is getting... Whoa, that's cool. All the funky signals with the wiggle on them. So this is the input to ADC. On the working meter, and here the input of ADC. Let's switch to the same mode. No, it's nothing. The wiggle still happens, but it's constant minus 13 volts. So much for that. level trigger works fine in this mode at least. So all that works. What else we got here? RMS converter gives us pin number what? U903. Pin number 3. U903, pin number 3. So we have plus 1.9 and 2 is also the same, and this must be 0. Yep, 0. Let's see what's in here. .9, 1.90, same. Okay. Let's see these guys. 16, 5. 1.9 and wiggle sine wave. Five, 1.9 and nothing. Actually minus 13, not nothing. Let's try next switch. 5. No, this is 8. 8, 7. That's the 0 and wiggle signal. So it's track and hold circuitry that seem to be dead. 5. This is DC output from the DC board, and this is the output to AD board. So the only circuit left is track and hold and multiplex into AD, at least in this mode. Because everything else we already tested and checked. 0. Yes, this wiggle is generated by all this magical stuff. And instead of sine wave and wiggle, we get minus 13 volts, and that is not correct. Let's see what we get at the input. Of this PMOS. Q904. Oh, plus 14. Oh, wow. That's a big signal. Yeah, that looks different. and that looks dead. This stuff is correct, whatever that pin is. Let's see. There is a logic chip nearby and a bunch of Zeners. There's a lot of stuff going on here. Let's see the logic chip. 009. Where you are? Come on. There you are. No, that's not you. Zero 001. I need 002. There. Pin number 8. Ouch. Bunch of stuff there. Pin number 9 and 10. It's just an inverter. Let's see, I think that works there fine. Yep. Inverting all right. So there are a bunch of transistors and 2 JFETs. Looks like they are JFETs. What they are? Oh boy. N4401, I believe. Yeah, those are bipolars, not the JFETs. Uh-huh. 3 and 2, let's see that. That is 3 and 2. Whoop. Yeah, the same signal. And 6. Nothing there, nothing there, nothing here. So I believe this is Q905 that we need to check. Where you are? 905. There you are. And there is a strange looking thing. Okay, there is interesting stuff. Okay, they replaced the current source with the JFET, I believe. And that is fine. That is that. That is that. So this is we have correct. Then the next. Wiggle, wiggle. And here we have nothing. have some craziness going on there. And that is just minus 13. And here, can't reach there. Just kind of sucks. Okay, though, so that's what I should get there. But instead, I get something else. There you go. And this guy is his custom part number. Here, 4391, I believe. Yeah, 2N4391. It's a JFET. I believe I have a couple of those. But I'm not sure it's the problem. That's the problem. Yep, the blue board is the custom one. So, should we go ahead and start shotgunning parts? Or we can check the Zener. That would be easy. CR 904. Where you are? 904. CR 904. Okay, so that sounds about correct. That's about correct. Zener is fine. There is a, is it a varactor? It's a strange symbol, 903. just next to it. Okay, that's what it does. And this one doesn't do anything. Which part this should be? Let's see, CR903. CR903, let's see the bomb. I'm sure I don't have that part. A2 assembly. CR904. Where you are? It's not A3, it's A2. (903), it's Schottky. Oh, okay. It's 1N5711. 1N5711. What is it? RF Schottky. And DigiKey have 13,000 in stock. (70 volt). Now the question is, can I put some other Schottky in there and see what happens? I have some diodes, not sure I have Schottky for the 2 picofarad capacitance. Or actually we can look up if A3 board or A1 board uses it and just steal from there. Because I have a bunch of those boards. Well, maybe not bunch, but I have some. I have Schottky for high current. But yeah, I don't think I ever bought small signal Schottky. Well, there is a little Schottky. MBR 0580. I don't know, we can look at the datasheet for that. It's also SMD, so, but it's a little one. Do I have any other Schottkys? Mostly Zeners. Nope, just that one. Let's see, 5711. Let's see for any on A1 board. Yep, there is one. Yay, it's CR109. CR109. Let's find it. Should be a blue looking one. CR509. Where you are? Oh, there is, I see a blue looking diode, but CR109, there it is. Let's get it out and put it in there. I wouldn't even bother removing the board because it's just 2 pins, so I'll just piggyback on top. They bend the pins, so it's hard to remove like that. There we are. There we are. Meter is off. Let's see if I can pull it. Nope. The pesky pins are bent in, so I'll have to snip them off. Five, 7, 1, 1. It's a ST part, by the way. Come on, you bugger. Get in. There we are. Let's see if the original is alive or dead. Maybe I'll just beep it with my good old Fluke 87. Whoop. Looks okay. 0.353 in one side and overload in another. Probably was fine. Nope, still same. It's not the diode. It's not the diet. There should be plus 5 volt at 904. Yeah. And some signal. Let's see what's in here. That is correct. Let's see what's on the R913. R913. Okay. Signal with bunch of stuff. And wiggle signal. There's just nothing. And here's our signal. Okay. So that side is fine. So this is okay. Let's see this current source, CR902. CR902 there. It's -13. -13 here. Here is some signal. Am I probing the right one? So hold on a second. Okay, some signal. There's nothing there. Nothing there. Why? GM402. Signal there. That makes no sense. R910. R910. I cannot find it. Anybody see R110? R10? R910? R911. Oh, there it is. Okay, that is correct signal. Both ends. Yeah, no problem there. But it doesn't make sense because that does not make sense. Why this signal is different? CR902. Huh? I think we should call it a day, probably. Essentially what happens is we have correct signal center in where is it? Whoop. Probably cannot see anything on this thing. The issue is somewhere in here, and we have the right signal from the input amplifier, main amplifier. All that stuff works in this synchronous mode, but something in here, instead of AC signal going to ADC, it goes crazy and just minus 13 volts DC voltage instead of around 0.1 volt AC. So this stuff is good, this stuff is good, this stuff is good. Something is in here is bad, or in here. So I don't think it will be very exciting to watch me doing this for next couple hours. And it's already 9 p.m. here. So it's getting late. So that's how the signal should like. With this wiggly stuff. And here how it looks on the bedboard. Just fixed minus 13 volts. Nine watts. Oh, you didn't see that. And I want actually to understand that part of the circuit before I start swapping those unobtainium JFETs. So, yep. It's an interesting one. Hi DevPom, you missed pretty much everything, but the unit is still broken, so that's that. And today we are suffering with repair of AC board from yet another 3458A. So we have the unit, actually the bed unit, originally that one on the left, with my good board in it, A2 board, and the bed board is in my good unit, this stuff, and I'm comparing stuff, measuring signals, trying to figure out what's going on. We snip some parts, solder some new parts. None of that helped. And it's pretty much going on like that. And to compare signals, I just supply 1 volt, 1 kilohertz from one of 5720s I have right there, and it's supplying to the scope, the sine line, and also the purple is channel 3, the one with the probe. So I poke around the circuit and see if it's what signals are different, what's not. What's the flickering wave? The wiggle wiggle? That's the bastard. So, where is my stash with JFETs? LS4392, LSK389, LS4392, LS170B, LSK489, LS4391. There we go. LSK389, LSK170, LS4393, and LSK170B. I think we will use one of these, LS4391. And replace that bugger, which is 2N4391. It's hermetic package, well, but I'm not sure if I have 2N. MOSFET and JFET. Uh, 2N4393, there, PN4391, but these are also in plastic package. 2N, these are 2N4392s, not quite the same stuff, nope, so yeah. And since I'm messing with the JFETs, I always use the ESD strap because JFETs are easy to kill. It's not a CMOS that you can hammer it with anything and it will live. Oh, okay, so there is another issue, I believe. I think the hermetic package and the plastic, they have different pinout, if I remember right. So yeah, there is that. Let's figure out what's the pin out here should be. So this is a gate. 499, 910. No, that's not the gate. That's pin number 1. That's the source. That's the gate, that's the drain, right? Where is it going? What? C905. Yeah, that's the drain. Let's see what's the pin out of LSK. It's LS4391. Asking what? What's going on? LS4391. Data sheet. Give me the data sheet. Buggers. SOT 23. Come on. My part is not SOT 23. It's the TO package. Thank you very much. TO 92. There we go. So drain source, okay. Yeah. Or no. Well, let's see. Bottom view. There we are. The dreaded JFET is out. Let's put the new one in. This is in the way. Bottom view, that's the gate. 910. There it is. I think I also put the diode back in. Or should I leave that one? Yeah, just leave that one. Just clean up the mess in here. Okay, let's see how it doesn't work again. That was a lot of beeping. See what's going on. Still broken. Yep. That was not that. Wiggle, wiggle. And in here, just -13. Then some craziness happening on the other end. So there are these current sources. CR902 CR and CR901. Where is the 901? There. Maybe this current source is dead? Because there is nothing else here. I can replace the current source with the JFET and a resistor. Because I can just beep them. What happened to neutron? Nothing happened. Still there. The article is all on the site. Okay, what's the business in here? So this J304, that's the one current source, and there is a diode looking thing on the other one. So J304. Whoop. What should we do? Steal some current sources from A1 board? Maybe? Are there any J304s? Little buggers. I think I'll need to check for the bomb. JFET. Oh, it's usually CR identifier. CR. Current source. Current regulator. Okay. And another current regulator. CR114 and there is 3 of them, CR10 and CR11. CR10 and 11. Let's see. I see CR10. And I see CR11. And question how much current they are. If it's 1 milliamp, then I'll just put this in here. So, let's see. CR10, CR11. Let's put that diode back where it belongs. Whoa. Don't fly away. So to check the current source, we can fire up our good old friend. Keithley 2400. Okay, let's not make a pool of water in here. There we are. So we can set current source, we can actually voltage source, 10 volts, 10 volts is fine, and the compliance, let's say let's say 5 milliamps, and output on. Let's measure current. We can also see the voltage. Yep, 10 volts. And let's see. Okay. Now we reverse the polarity. 1.2 milliamps. Well, that's good enough for America. And 1.25. Not exactly 1.0, but I think this is okay for test. So we can go ahead and swap some of the current sources. They look like diodes, but it's just a junction with the limiting, so it's whatever voltage you supply across the terminals, it will draw just around the current it's designed for. So yeah, let's get the fume extractor going. I don't want to breathe all that crap. There we are. One is gone. So the okay. Nine, 10. Okay. I can actually just probably lift the second one and test it. $105. Yep, 108. Let's see this one that I just desoldered. Okay. There is nothing. Zero. That's interesting. Did we find that part? Oh, cool. And let's see if changes anything. Where's the Actually, we can put a cover over this section because we know that works just fine. No need to have a reason to break any of those parts. So let's do that. Let's see if we get any difference. Okay. That's different. Interesting. Let's see the set ACV sync. And we're still broken, I believe. Let's see some signals. Nope, still minus crazy volts. But A to D does not get minus 13 volts anymore. All right. What else we can do? Let's see what's again we should be getting. Should have the squiggly, jumpy. The schematics. And output pin 6. What? Yes. Pin 6. Squiggly, jumpy. Here we have nothing. And there we have nothing. Just slowly dropping like minus 1 volt, minus 1.1. So it's just some crap. Let's see again. Transistor. What's the output of our buffer? What? Pin 2. Where is the signal? Okay, my bad. There is our signal. And there is our what? 7. That's our signal there. Minus 18. Okay. We get signal here. We get minus 18 there. Signal there. Nothing there. Nothing here. Nothing there. Q906. There is something there. Okay. Well, we can run the self-test just to see how bad is that. Reset. Clear errors, self-test. I don't need to remove the cover when I take the A2 board because it's not mounted to the frame. It's mounted only to the PCB. And the part number I just replaced is J304, 1 milliamp current source. So we already fixed the issues with DC voltage resistance, but we have the issue with AC voltage that does not want to be fixed. And the issue is flatness dot convergence 198. And the same happens if you do a AC. There, fails right away. And there we have it. It also have a bunch of crazy values in different ranges. So yep, so instead of signal, like you saw on the good board, we just have minus 13 volts DC voltage and nothing works. All right. Is this is Agilent 3458A with the option Fluke HFL. There is no such thing as Philips 3458A. And the unit we're actually talking about is the unit in repair is this one. This is my test unit. that we just have swapped the good board from this unit, put in here to test that all the other boards work fine, which they do, and this unit have the bad board from this unit. So all the AC issues that failing is from this A2 board. Can you snip one lead and set the voltage to something normal to check if the reading changes? Yes, of course you can do that, and it will read just fine because everything else in the instrument is okay. So there is no much point that I see in doing that. Because we're trying to repair the broken board, not test other boards. We already did that. There, so. Any other questions? Because I think we should finish this one up and call it a day and call it a failed repair because we didn't fix it. Let's put the good board back into the unit and check that it's working fine. Run the self-test. Got the service manual. Well, the service manual and component level repair is available on xdevs.com/fix/HP3458A, which was the first article about 3458A repairs that I did some years ago. And that article have links to all the service notes and repair level manuals, including assembly level and component level. So it's available to download without any registration or any other crap. So as usual, I have a lot of test equipment repair articles, notes, and overall content, as well as metrology related stuff like LTZ1000A voltage references article, how to build one, how to test one, what the usual issues could be, and including the BOMs, component lists, test results for resistors, and many other related metrology stuff on xdevs.com website. And also there is IRC for live chat, which is running on our own server. You can get access to that by going to https xdevs.com/chat. But I would recommend getting the IRC client, such as MIRC or HexChat or some other ones, to run and connect directly to the server. It is the domain name for the server is xdevs.com, and port is default 6667, I believe. And I'm also active on EV blog forum, so you can find some stuff I post there. Although recently I've been busy with all the other projects and things, so didn't post as much. This should pass just fine, because all the other hardware is in this unit is working. I'll need actually to replace the fan in it to the faster fan I always use in 3458As, because obviously when I'm running other test equipment like somebody can see right in here. The fan noise of 3458A is not really noticeable compared to all the other gear, especially 5720s and the 5725 booster. Those are some noisy units. So that's what we have in lab, and it's running 24/7 to ensure the accuracy and maintain to the highest precision possible, because metrology and calibration equipment does not like to be turned off and turned on, because every time you do that you cause the stress to the components, and you cannot predict the drift and changes of the measurements from the power cycles. So instead of trying to minimize that, we just keep the equipment running 24/7, so it's always stay at constant temperature conditions, constant power conditions. So that's how it's done. What's the mainframe on the shelf? Which mainframe? If you're talking about the one in the center, that's Agilent 4142B parametric analyzer, which is essentially a glorified, fast multi-channel SMU. I have 4 SMUs in it. Model number 41420A. Those each SMU can source up to 200 volts and up to 1 amp. And also they are all equipped with triaxial inputs. So you can connect special wiring and do from like nanoamp level measurements till the multiple amps. So yes, that's the one unit labeled for number 14, which is GPIB number for it. There is a closer look for it. I rarely use it, but for those moments when you do need it, it's a very invaluable tool. It's quite old, but still very capable instrument, especially with the remote control over GPIB, because it doesn't have any display or screen, so you don't have user interface for it other than remote control over the software that I write. There is the temperature chamber, that box over there shining in, and there is the main calibrator with the booster for it. Still running. How many kilowatts I use to run constantly? Well, usually the power consumption during summertime, like right now, with the air conditioning running, because of all the heat waves and all that. So it's around 2.4 megawatts per month. And in winter time, when it's cooler, it's around 1.6, 1.8 megawatts per month. Yeah, 5725 was quite expensive. It's not as expensive as the calibrator, but still. I think I paid around 6 grand for it. And it's not used very often, but it's an invaluable tool for AC voltage calibrations for some of the instruments like Keithley 2002s and Fluke 8508, the Tron 1281, AC voltage meters, and some higher power stuff. I also like 5725 because it supports both extended current up to 11 amps for both DC and AC, and also high voltage AC stuff. I would love to have 5205 and 5210 as well, but those are huge beasts, and knowing that I'll rarely use them, so far I think I'll be staying happy with 5725. There is the AC test. That's how it should pass. Okay, so we can switch this, and we get our 1 volt just fine. That's what we should be reading. Okay, so that's it for now. Thanks everyone for stopping by and hanging around with all this stuff. We'll see you all some other time.